All right, so now that we've plowed through all of that math, time to apply it. Okay, so I've put my handout on Blackboard for you guys to read along a little bit, although I'm not going to go through this line by line. So here's the handout. We go through Faraday's law, Lenz's law. I'm not going to review all of this information. Here are some equations to help us remember what inductance is. Again, not going to spend any time here. We've got another equation we need to learn. Also, something I haven't done much at all this term is refer you back to Delmar's textbook. We are going to be working on units 16 and 17 this week. Okay, 16 is about inductors, and then 17 is what we're really going to get into here in terms of the math. So I suspect I'm going to break this up into smaller videos again, maybe 2 or 3 or 4 short ones to start with, leading into a much longer final video, which will be that chapter 17, which is really getting into circuit calculations, okay, back into like what you did last term in DC, but now in an AC circuit. Okay, so the conversation here is, and I have said this before, but let's say it again, when you did all of that math last term in a DC circuit, there was only one type of load, okay, and that type of load was a resistor. In a DC circuit, that's the only load that matters. In an AC circuit, we have 2 other types of loads to consider in addition to just a resistor. One is an inductor, okay, which is a coil of wire, okay, and the other is a capacitor. And so we've looked at both the inductor and the capacitor a little bit, but we're going to spend a lot more time there now, okay? So let's start the conversation here with the inductor in an AC circuit. We've looked at it in the DC circuit the instant that the switch closes. Now let's look at it in an AC circuit. So let's pull up these images that we've seen before. So here for a second is a review of what we've already looked at, what happens when we put an inductor in a DC circuit. So we started the conversation with just a resistor, never mind an inductor. Remember what happens the instant you close a switch. You have the full 20 volts resulting in 2 amps of current flowing through this circuit with a 10 ohm resistor. Instantly, close the switch, there's the current. Compared to when we replace that resistor with an inductor, because the coil of wire, okay, is an inductor, what's going to happen the instant we close the switch is we're going to start to build this magnetic field, okay? And the expanding magnetic field gives us relative motion between the field and the conductor, the coil of wire, which is going to induce a voltage back onto the wire or back into the circuit. Okay, and that induced voltage, because of Lenz's law, which talks about the concept of inertia, it's going to push back against the applied voltage. Okay, the result is that it takes time for the current to build in this circuit with a coil in it, with an inductor in it. Okay, let's look at the next image. Here's the expanding magnetic field. Okay, here's the applied voltage. The instant that we close the switch, we get this 20 volts of applied voltage. Okay, but what's going to happen is immediately we're going to start to see an expanding magnetic field as a result of current flow, which is immediately going to generate this induced voltage pushing back against the applied voltage. And there's a notion here of rate of change that we have to consider. Okay, and so initially the expanding field is expanding very quickly and we get a great deal of induced voltage. Okay, but then over time, as the rate of change slows, the induced voltage slows and we get an increase in the effective voltage. Okay, here's the current in our circuit, and in terms of rate of change, you can see that there's a great rate of change initially, okay, which is why we have a fairly low current, because we have a great deal of induced voltage. Means we have fairly little effective voltage, the difference between these 2 arrows. But as the rate of change slows, the induced voltage gets smaller, and so the effective voltage grows to the point where when we reach our 2 amps, it's because we have the effective voltage is now the applied voltage. And we're pushing a full 2 amps through the circuit. Okay. Now this is still in a DC circuit though, right? The only time where this conversation can be had, the only time that this is interesting, is the instant that we close the switch. Now, let's finally move forward to what happens when this is always changing. So remember that we're now dealing with the sine wave, okay? And so we have a period of time where things are growing. Now, these arrows are labeling current. I would say we should start the conversation talking about voltage. So there's more voltage in the circuit to a point where we peak with the amount of voltage that's there to push current, and then a reduction in the voltage to a point where there is no voltage, and then the voltage starts to want to push the current in the opposite direction. And it grows and it shrinks. So it's constantly changing. So it's like the instant that we close the switch, except that it just goes on and on and on and on and on. Okay? Which means that this applied voltage is always changing, which means magnetic field is expanding and collapsing. This induced voltage is always changing. There's going to be a constant flux in the current as well. Okay? So here's what we're looking at here. We have an expanding magnetic field as the current grows. We have a collapsing magnetic field as the current falls off. The next thing that we want to look at is this applied voltage compared to the induced voltage. So if we look at the sine wave that is the applied voltage and the sine wave that is the induced voltage, they are out of phase by 180 degrees. So they are exactly opposite. Okay, they are always, always, always pushing against one another. Okay, so the question then is, what is the result to the current? And this image that you have in your handout, I'm not really crazy about it, so let's go back to hand draw an image that does a better job, I think, of explaining this induced current. So I want to compare that current to the applied voltage, not the induced voltage. The image that you see there on your handout is the induced voltage. I want to refer back to the applied voltage. So there's the applied voltage. That's what's being provided by the power supply. We know that the induced voltage is 180 degrees out of phase. It's doing the exact opposite. It's pushing back against it. Okay, the question is, what is the result of the current in this circuit? Well, we saw in the DC circuit, the instant you close the switch, you immediately have your voltage, but it takes time for the current to build to whatever, in the image we saw it was 2 amps, but whatever the full current might be. Okay, so the notion is that the current gets delayed. Okay, despite the fact that we have voltage here immediately, the current doesn't follow the same trend. Okay, if this was just a resistor in the circuit, then yes, the current with a different magnitude would be in phase. All right, it would have the same 360 degrees. Okay, we start at 0, we peak at 90, we return to 0 at 180, we have a negative peak at 270, okay, and we finish the circuit, we finish the cycle at 360. If all you have is a resistor, that's the result. But because it takes time for the current to build as a result of that induced voltage pushing back against the applied voltage, giving us only the resultant voltage, so you've got the applied voltage, you've got the induced voltage, you have the effective voltage left to actually push the current. And it takes time for that to build because of the Lenz's law inertia kind of effect, pushing back against the change. And so the result is, and even if you can't wrap your head around the whole notion behind it, and I'm not sure if I'm doing an adequate job of explaining it, the end result is this. This is what you need to sink your teeth into, okay? And the end result is that you get a delay in the current, okay? And so the current sine wave looks like this. Okay? Now it's said that in a perfectly, in a pure inductive circuit, the current will lag the voltage by 90 degrees. Okay, now there's our 90-degree triangle, our right-angle triangle, so that's a good thing. Unfortunately, there's no such thing as a purely inductive circuit. We can talk about it theoretically, but realistically, every single circuit is going to have at least the tiniest little bit of resistance, because of the wire that's required to build the circuit is going to have a resistive value to it. However small it might be, it's going to be there. So there's never going to be a purely inductive circuit where the current lags the voltage by a full 90 degrees. It's going to be a combination of induction and resistance within the circuit, and therefore this lag, the current lags the voltage, will be something a little bit less than 90, at least a little bit less than 90. Okay, so let's come back to this final statement. So this is it. I just said it. Now I've written it down for you here. In a purely inductive circuit, which is theoretical, okay, in a purely inductive circuit, the current lags the voltage. So here's why we spent time talking about the concepts of leading and lagging, because this is what's happening. The current lags the voltage by 90 degrees. Now, it would also be true to say, because we learned this, we could say that the voltage leads the current by 90 degrees. However, we don't say it that way. Okay, we always want to talk about what is happening to the current as a result of the voltage, because the voltage is sort of the, I don't want to say the constant, but it's the force that's provided by the power supply, and then the current results from both the voltage and the type of load in the circuit. So what is the current doing relative to that voltage? Well, the current lags behind the voltage by 90 degrees in a purely inductive circuit. Okay, so let's leave this lesson right there, and I'm going to move on to the next idea in a separate video.